All right, so we finished up most of the mechanics, just talking about how things move and why they move the way they move. Um, we're going to move into heat and thermodynamics. So first, we're going to talk about the basics, sort of the initial definition of temperature and heat transfer, and then that's going to lead us into thermodynamics later. um, the place to start with this is with Count Rumford. Um, he was actually born in, I believe, Massachusetts. He was born in America during around the time of the American Revolution, and then he defected to England. Yeah, he was American born, but spent most of his life in like the UK and Germany, I believe. Um, but he was very bright, had a lot of side projects, and he's sort of the father of uh, modern thermodynamics. So he was actually put in charge of making cannons using essentially just a large drill bit to bore them out and make the muzzle for the cannons. And he noticed that there was a whole lot of heat coming out of or coming off the drill bit. He also noticed that if the drill bit was dull, the heat coming off was even greater. So the whole idea here was essentially he had a horse-drawn lathe or auger. Um, Essentially, as the horses walked around in a circle, they did work, which would use a gear mechanism to essentially just turn a bore. And you can see that this axle is being rotated. And essentially, that would turn the drill bit and drill down into the cannon muzzle. So he sort of put together when work is being done, then heat is being produced. And it wasn't that the metal itself was releasing the heat. That's the metal was not the source of the heat. The work being done was the source of the heat. So this sort of flew in the face of the idea of how heat worked at the time. So at the time they had this caloric theory of heat, just like calorie. Essentially, they thought, oh, like heat is this mysterious caloric fluid, and when you like start scraping in the cannon, then this mysterious heat fluid gets released. So Rumford was able to say, no, that's not the case. It's not the heat being released from metal, it's heat coming from work being done. Um, Taking it back to grade school, before we can talk about temperature, let's talk about the four states of matter. So we have a solid, which is just a phase of matter characterized by a defined volume and shape. So you'll remember that a solid has a volume that you can calculate and it has its own shape. You can see that here. The atoms in a solid are usually nice and well arranged and they're bonded. In a liquid, so the liquid is a bit of a in-between phase between a solid and a gas. So when you move to a liquid, it's matter that it does possess a definite shape, definite volume. Sorry, it possesses a definite volume, but not a definite shape. So whatever you put water in is going to take the shape of its container, right? You can see that here in this beaker. We could have a beaker shaped like the state of Maryland, and when you pour in water, the water is going to also take the same shape. If we move on to a gas, so this is the phase of matter beyond liquid, and it has no definite shape. And the particles, they just fly around, they move freely. You can see that here, and all these particles are moving around. We can also go up one more step here. If we wanted to talk about plasma, that's essentially a gas that has got so heated or so charged that some of the electrons start flying off of the atoms. So then if you have a neutral atom, you knock off an electron, suddenly you have a positive atom in there. So a plasma is essentially just a charged gas. So this phase of matter is mainly at high temperatures. So in undergrad at App State, I actually worked in a plasma physics lab in the physics department. And when we would trap the plasma that we were studying, we could calculate its temperature, and the temperature was usually like hotter than the surface of the sun. So if you have a plasma, you have a very, very, very hot gas trapped somewhere. All these phases of matter, they contain in some way jiggling atoms or molecules. Even if they're in a solid, these things can still move around a little bit. Because these atoms can move around, well, they have to have kinetic energy, right? Because we know that any sort of motion, if there's motion, there's kinetic energy. So if we have moving atoms, we have to have kinetic energy, or they have to have kinetic energy. The whole idea here is that if these atoms or molecules do have kinetic energy, remember that's 1/2 mv squared. There's our velocity, there's our motion. If these atoms have kinetic energy, the average of all those little individual kinetic energy values, if we average those up, this is actually what we detect as warmth. Okay, so when you feel heat coming off something or you feel warmth, that's actually, you're just feeling sort of the overall average of the speed of all these atoms. Now, the quantity that we indicate warmth with respect to some standard, and this is going to be important later. So this quantity, how we assign a number to warmth, is called temperature. So really, temperature is just a measure of average kinetic energy. So all those times when you were a kid and your mom was taking your temperature because you were sick, what that thermometer in your mouth was doing was actually measuring the average kinetic energy of all those atoms in your mouth. Or if you're cooking a steak and you want to make sure you get it cooked to the right temperature, I like my steaks medium rare, so that's going to be 135 degrees Fahrenheit. When you stick that thermometer in, you're measuring the average kinetic energy of all those atoms hitting the sensor. Now, molecules can move around in multiple ways. They can rotate or they can vibrate. So we have this translational motion, but we also have rotational motion, where these molecules can turn. And then the bonds between the atoms making up the molecule can also move, right? So these are molecular bonds. So when we talk about temperature, it's really only defined by the translational motion. So this is our temperature. Let me try that again. That looked gross. There we go. Oops. Okay. Now, earlier I said that we have this temperature with respect to like some standard, right? Here, yeah, with respect to some standard. So the whole idea here is essentially when we express temperature, we assign a number to it. Okay, it corresponds to a degree of hotness or coldness on some chosen scale. So we sort of get to decide how we represent temperature. It's a little more nebulous and a little less defined, more so than other things, because this is always relative to something else. We have to choose a scale that's built off of something that's relatively chosen. So, for example, a lot of times scales will use like the boiling and freezing points of water. We pick those two things to make our scale. Now you can pick whatever you want to. You can pick, the temperature that your grandma thinks is cold outside as the lower end, and then the temperature when you start sweating as like an upper end. It's all relative. But when we actually decide on the scale we use, what we can do is use the fact that almost all materials expand when the temperature is raised and contract when their temperature is lowered. So if it's hot, it's going to expand. It's colder, go blue for colder. It's colder, it's going to contract. So what we can do if we want to measure on a scale of our choice, we can use this idea of expanding means hot and contracting means cold, and essentially measure like an expanding or contracting liquid. So that's why you'll see like a mercury thermometer. Usually they have a little bulb on the bottom. So what happens is when it gets hot, the mercury in the bulb expands and goes up, and then you can read it. So whatever scale we assign is going to correspond to the height of the mercury in the tube, because it's going to expand when it gets warm or contract when it gets cold. And that's how we can leverage this physical feature of nature with things expanding and contracting to actually put numbers to what that expansion and contraction means by measuring the temperature. Which leads us to an important question that you have to deal with a lot, especially if you travel internationally. How are temperatures measured in Celsius converted to Fahrenheit? I'm sure you all have seen both scales before, and then vice versa. How are temperatures measured in Fahrenheit converted to Celsius? So both of these, Celsius scale and the Fahrenheit scale, someone's come up with measuring points for both of these, and then put them on a thermometer. And they got to pick whatever scale they wanted to and define it however they want to. So we do need to figure out a way or figure out how that these two scales are related. So once we assign temperature to a scale, we have to pick these physical things. So with the Celsius, the scale is essentially the 0 point, because they wanted it to be the 0 point, is the freezing point of water, which is 32 degrees Fahrenheit, and 100 on the Celsius scale is the boiling point of water, so the other end of the spectrum for water. Okay, now we can see that over here. We've got, let's see, right here is the first point of our scale, 0 degrees Celsius and 32 degrees Fahrenheit. It's the freezing point of water. And then on the other side of this thermometer, we have the boiling point of water. Something you'll notice that the Fahrenheit increments are closer together. So if you look here, this distance is only 10 degrees Celsius, but a very similar distance, so this is almost the same, is actually 20 degrees. So here you got 10 degrees, here you got 20 degrees. Essentially, the Celsius numbers are a little more spread out. So you sort of, how to say this, you get a little more bang for your buck if you're just looking at integer numbers, so no decimal places. You get more slots in the Fahrenheit scale than you do with the Celsius scale, because the whole number increments are a little more spread out in Celsius. But it's fine, because both scales function just fine. They both measure temperature just fine. And converting between the two is actually not that bad. So if you want to go from Celsius to Fahrenheit, you can use one of these two equations here. You can plug in your temperature in Celsius, and essentially you just multiply by 9/5, and then you add this offset of 32 degrees. And that gives you your temperature in Fahrenheit. And then to go backwards, if you have temperature in Fahrenheit, but you want Celsius, you can use this other formula here, just a quick plug and chug. Don't mix these two up. It's very easy to, but notice one of these, the number out front, the coefficient is 9/5, and the other one is 5/9. So do be careful. Something interesting to think about is that a thermometer really just measures its own temperature. Like, we use them to measure the temperature of other things, but really what's happening is if you have an object, we'll call it object A, and then you want to measure the temperature of object A, so you put a thermometer on it or in it. This will be our thermometer, object B. Really what's happening is you're waiting for these two things to equilibrate, right? You're waiting for the temperatures to change and be the same. Once that happens, when you read the thermometer, you're really reading just the temperature of the liquid inside. You're working under the assumption that the temperature of the liquid inside the thermometer is now the same as object A. Yeah. So basically, you just have to wait for thermal equilibrium to be established for that to happen. And then, if you know the temperature of the thermometer after thermal equilibrium has been achieved, then we know what the temperature of the object is. Something to remember, thermometer should be small enough that its temperature before the measurement won't affect the temperature of the object being measured. So if you're trying to measure like a little raindrop and you have a really big thermometer, well, if you've been holding this thermometer in your hand, it's warm. The raindrop might be cold. So as soon as you put this giant thermometer in this tiny raindrop, well, that's going to bring up the temperature of the raindrop and you're not going to get a good, accurate measurement. So a thermometer should be small enough so its temperature before the measurement won't affect the temperature of the object being measured. And do keep in mind that thermometers only measure translational kinetic energy, so this one. And if you think about it, that makes sense, because if you had a bunch of molecules that weren't moving around and you stick your thermometer in there, how is the thermometer going to know what the temperature of these molecules are? Because they're not actually touching it. So that's why you were really only measuring the translational motion. All right. Celsius and Fahrenheit, I'm sure you guys have dealt with before. But let's move to the Kelvin scale. This one is less known scale, but it's used a lot in the sciences. So this is sort of the go-to temperature scale used by scientists. It was developed by, what was his name? I just know him as Lord Kelvin. But this scale is really neat because it's not calibrated in terms of like freezing and boiling points of water. It's actually calibrated by the idea of absolute zero. So the number 0 is assigned to the lowest possible temperature. So there's actually a minimum temperature out there in the universe where you could actually get so cold and have so much energy removed that a molecule or a substance literally has no more kinetic energy to give up. Like it's given off everything it possibly can. And that is called absolute zero. So this is essentially where almost all molecular motion stops. I think some weird things happen with helium, maybe. I think helium might actually have a little motion in it at absolute zero. But other than that, maybe it's hydrogen. But other than that, almost everything stops completely. There's no more energy to give up. So that is actually where we start our 0 point for Kelvin, which means there's no negative numbers on the Kelvin scale. You can't go negative Kelvin. So you're at 0 Kelvin and you work your way up. Also note, and this is important, the Kelvin scale isn't measured in degrees. So this is 0 Kelvin, but this same point at absolute zero in the Celsius scale is negative 273 degrees Celsius. So this one has degrees, just like Fahrenheit, but this one, no degrees. It's just the unit. Another cool thing about the Kelvin scale is it's literally the same increments. So you'll notice that these increments here, like from here to here, or we can even do a big increment from here to here. Where did I drop that? About right here. The increments are the same in Celsius and Kelvin. So +1 degree or +1 Kelvin is the same as a +1 degree Celsius. Unlike Fahrenheit, which is like 9/5 or 5/9, it's got that weird fraction. The amount of change in the Kelvin scale is going to be the same as the amount of change in the Celsius scale, but there is an offset. The scales are shifted. So if you have a measurement in Kelvin and you want to go to Celsius, all you have to do is just unshift it, right? You just subtract off that 273 shift. So it's literally the same increments, they're just offset. So if you want to make that change, subtract off the offset. And that's how you convert from Celsius to Kelvin. All right. So that's the definition of temperature. That's how thermometers work. We're talking about measuring temperature and translational motion. Now let's talk about what happens if we have heat, if we have warmth, and it flows to something else, okay? We talked about the thing itself. Now let's talk about how and why that thing changes. So if you put an ice cube on a hot piece of metal, the ice cube warms up and melts. The ice cube warms up and melts while the metal cools. So the metal cools down. Clearly, energy is being exchanged between these two things, but in what direction is it changed? The idea here is essentially the direction of spontaneous energy transfer is always from a warmer object to a neighboring cooler object. So hot to cold. So in our example, it's going to be metal to the ice. So the transfer of energy is called heat. Okay, so temperature is not heat. The change in temperature is heat. Right? You can think about heat as sort of like a velocity. If you're not moving, you don't have a velocity. If your temperature is staying constant, if you're not transferring energy, transferring heat, you don't have heat. Okay, matter does not contain heat. Heat is a transfer. Okay, now the question is, what is being transferred when we have heat that we can measure? So internal energy is the grand total of all the energies inside of a substance, okay? Like I showed on the previous slide, you can have translational motion, rotational motion, vibrational motion, lots of things to be had here. The whole idea is that if you sum those up, That is your internal energy. So all of those individual energies. So we could actually say a substance does not contain heat, it contains internal energy. And then heat would be the change in the internal energy. So when a substance gains or gives off heat, that's the internal energy actually increasing or decreasing. Now, when two things come into thermal contact, again, heat flows from hot to cold. So the higher temperature substance gives off heat, the lower temperature substance gains heat, right? So we've got a minus heat here, gains heat here. Those supposed to be parentheses. I know they look like crap. That's my bad. So this is not necessarily a flow from the substance with more internal energy to a substance with less internal energy. So we're talking about just the temperature, higher temperature to colder temperature, not high internal energy to low internal energy. That's not necessarily the case. So make sure you understand the difference between these two. Heat flow is based on temperature, not the total internal energy. Also, how much heat flows actually depends on the amount of the substance as well as the temperature difference, right? Really hot to really cold should go fast. But if there's way more of one of those objects than the other, that's going to play a factor too. There's also mass that's going to affect this. You can think about it in terms of like a barrel full of hot water, right? So that's a big mass, lots of water. This will actually transfer more heat to an object than just a cup full of hot water. Notice it's a lowercase m for a little mass. So the more mass you have, even though both of these things are hot, the more mass you have, there's going to be more heat transfer. So this one is our winner because there's way more mass. All right, let's look at this one example real quick. Suppose you apply a flame to 1 liter of water for a certain time and its temperature rises by 2 degrees Celsius. If you apply the same flame for the same time to 2 liters of water, how much will its temperature rise? Okay, so we're adding heat to 1 liter of water. For a certain amount of time. So it looks like when we do, and we get a temperature change of 2 degrees Celsius. Now, we keep the same flame, okay, so the same amount of heat for the same time, but this time we apply it to 2 liters of water. So the only thing that's changed is we've doubled the amount of water. So how much will the temperature rise? And the answer here is the temperature will only rise by 1 degree Celsius. Remember in the previous statement, it was 2 degrees Celsius. So we double the amount of water, we cut the heating in half. And the whole idea is when we start heating the water the first time, all this heat gets divided up to all these molecules, right? If we double the water but keep the amount of heat the same, all this heat is divided by 12 across twice the number of molecules. So that's why you only get half the temperature increase. So this one would be plus 2 degrees C, but this one is only plus 1 degree Celsius. So essentially applying the same amount of heat over more stuff is going to cause less heating or less temperature change. Suppose we have an iron tack and a big iron bolt. So a little iron thumbtack and then a big iron bolt. Okay. Both are red hot at the same temperatures and are dropped into identical containers of same temperature. Okay. Which one raises the water temperature more? Well, it looks like we're going to have a small iron tack with a little baby mass and then a big iron bolt with a much larger mass. Same temperatures, and the water that they're dropped into is also the same temperature. So really the only thing different here is the mass, little mass versus big mass. Same material too, they're both iron. So it turns out the iron bolt has more internal energy because there's more of it, there's more mass. So there's more mass to store that energy. And because of this more energy, this more internal energy, this more mass, what you're going to see is that the temperature of the water with the iron bolt will change more. So the iron bolt water will change more. And that's because there's more mass. All right, we need to quickly talk about measuring heat. So the whole idea here is since heat is energy in transit, we can actually measure it in joules. Just like work is measured in joules. Kinetic energy, also energy in transit, measured in joules. So since we, again, have energy in transit, we can say heat's measured in joules. However, in the US, because we like to do things differently than everyone else, we actually use a unit of heat called the calorie. You can think about that just like a food calorie. That's also a unit of energy. So the calorie is defined as the amount of heat required to change the temperature of 1 gram of water by 1 degree Celsius. Okay, so if we had my water, if we had 1 gram of water and we want to increase the temperature by 1 degree Celsius, we would have to add 1 calorie of energy to do that. That's the definition. However, the method of determining the amount of energy provided by a particular food requires the substance to be burned. This is called calorimetry. I might have just butchered the spelling of that. But I've posted an optional video of how it works. Actually, see if I can erase this. Perfect. Let me try to see. Okay, so some of you exercise science majors in the class might be familiar with this. The whole idea here is if you want to know how much energy is in your food, and you want to measure it in calories, and a calorie is just a measurement of heat, you can burn the food, and there's a special way to do that. You can see in the video. And then you can measure the heat released by the food, and that's how you get the amount of calories in food. You literally burn it and then measure that off-put heat. And that's how you get your calories, because calorie is a unit of heat or energy transfer. Something to remember is that the unit of food or the unit of calories used on labels is actually the kilocalorie. And that's why you'll always see it, if you can see it here, that's why you'll always see it capitalized, because a food calorie on a bag, 1 food calorie is actually 1,000 regular calories. So here on my favorite snack, potato chips, the 160 food calories is really 160,000 regular calories. So that's, do keep that in mind if you're looking at this on food wrappers and you're maybe doing a problem in the problem set. The food wrapper calories are 1,000 regular calories. And if you want to relate a calorie to a joule, 1 calorie is a little over 4 joules of energy. All right. We'll stop there. All I wanted to talk about this time was just temperature and heat transfer. Next time we'll actually talk about, instead of just how the amount of stuff changes heat transfer, we're going to talk about what that stuff is made of and how its composition will change heat transfer. But until then, if you have any questions or need anything, please feel free to reach out and let me know.